Okay, so today we're going to look at magnets, and on the board are, or on the screen are 4 anagrams. Hopefully you've worked them out. The top one is iron, the next one down is cobalt, the next one down is nickel, and then the bottom one is steel. And then the challenge question is which one is the odd one out and why. Now I'm aware that you won't be able to tell me which one or the why, but you should be able to tell me which is the odd one out. I'd just like to point out this is the higher year 10 webinar as well, and if you do have any questions or if I missed something or you want it explaining, Mr. Collins is in the Q&A question box area answering questions for you. So I'm just going to launch the first poll for you. So which one was the odd one out? Was it iron, nickel, cobalt or steel? I'll give you a few seconds to answer that. Interesting answers. Doo-ba-doo. I'll give it a few more seconds because I can see about 65% of you have had a vote. Okay, and I'm going to end it there, and I'm going to share the results. I'm then going to explain which one is the correct answer. So the majority of you actually went for cobalt, and that's actually an element. So iron, nickel and cobalt are actually elements, and steel is the odd one out because steel is an alloy. It's actually made of iron and carbon. So hopefully that makes it clearer. Maybe you pick cobalt because it's one of those weird elements we don't hear very much of. These are the only magnetic materials that there are. So iron, nickel, cobalt, steel. Anything else is not magnetic. And that hopefully is a bit of a recap from when you did this back in year 7, year 8. Okay, so first bit of what I want to run through today with you is just magnets. So the key features of a magnet, permanent and induced magnets and the earth, and why induced magnets can actually lose their magnetism. So that's the first bit. And then the second bit, I'm going to move on to electromagnets, which are funky. So this is a recap slide to help you describe the key features of a magnet. Okay, and at the top left, we have got 4 little pictures of magnets, and you should recognise that this is the standard. We have the N for north, we have the S for south, and we've got north and south. And when you put 2 opposites together, they attract. And then when you put 2 of the same together, be it 2 souths or 2 norths together, they repel. That should be hopefully basic key stage 3, remembering that they attract if they're opposite and they repel if they're the same. And then on the bottom here, we've got a fields line diagram, and I'm going to go over that in a bit more detail on the next few slides. But just to check we're all good, I said I've got a few polls. I've actually got 3, and the first 2 come quite quickly. This is the first one, second one, sorry. So do north-south magnets attract or repel? Or if you're not sure, go for not sure. Just want to make sure we've got the basic fundamentals sorted before we move on to the trickier bits. Just give you a few more seconds. You're going super, super fast, as I'd imagine on this. Dooby-dooby-doo, dooby-doo, dooby-doo.
A quick one, Miss Wanstall.
Yeah.
One that I've seen come up in exams before. Could you describe how you'd do an experiment to figure out which a north and the south pole of a magnet was?
Do you want me to describe that, sir, or are you asking them to?
No, I think if you could just run through that, that's something I see happen a lot. The poles is often a sort of a foundation kind of topic, but that's where it might come into higher, which takes this idea and applies it in a slightly more difficult context.
So normally it would be you have the magnets, and you can get a magnet where you know the north and the south, you can put them together. If they attract, repel, then you'd know you'd have what's a permanent magnet with the sides. And then isn't there the other one where you get the magnetic material and it doesn't attract and repel, sir?
It will attract because it's magnetic, but the key idea is you only get repelling happening when you have 2 things that are magnetic and they have the same poles near each other.
Right, thanks, sir. You'll notice I'm going to get Sir to jump in quite a bit on this one because he's like the master expert. I'm going to end that poll and I'm just going to share it, and you are all spot on that north and south are going to attract to each other. So well done, you guys. Okay, so moving it on. Magnetic field lines. So when you put iron filings around a magnet, you can see these wonderful magnetic field lines. And although this looks a little bit messy on the picture, you can see that there are some lines here, and then there's some coming out of north and of south, and then round here. Okay, and it's because those iron filings feel the effect of the magnetic field around that magnet. They feel the force of it, and it's a non-contact force because it's there. Just wanted to put that out because you should have done forces and contact, non-contact forces. So it's just a little throwback to that. This is with the field lines drawn on, and there are some very important things you need to be aware of with this. So you need to be aware that the magnetic field is strongest at the poles. Okay, so strongest at the North Pole and at the South Pole, and then weaker in the middle. And you also need to be aware of arrows. So if you ever get asked to draw a magnetic field diagram, it's important to remember to put the arrows coming out of north, going round to south, and then back into south. So out of north and in at south. And then I've just got this picture here, which is what we'd expect you to draw. So you can normally, I think, get 1 mark just for drawing the loops and the lines, and then you get second marks for making sure you've got those arrows coming out, going round and coming in at south. So out at north, in at south. And that is essentially your basic magnetic field lines diagram. Hopefully we're all good on that. Okay. Now, permanent and induced magnets. Okay, so essentially the way I remember it, permanent, it means it's always there. Okay, so it's permanently magnetic like the core of the Earth, and an induced magnet means that it can lose its magnetism. Okay, so here we've got a picture at the top of a needle, and that is a magnetic material, but you can make it magnetic by rubbing a magnet that you've got along it so that it becomes magnetic, and then it can pick up paper clips. And there's an experiment where you use a needle before you've made it magnetic to try and pick up paper clips. It won't. You rub a magnet along it in one direction, and then it's able to pick up the paper clips. And I'm going to do a little bit more on what's going on with that here. So here we've just got the before and we've got the after. So you can see all these little mini magnets, little mini domains in the needle, which mean it is a magnetic material, but it's not a strong magnetic material. And then by rubbing that magnet along it, you cause all these little mini domains to line up, and then that makes it become magnetic. So it's been induced into magnetism. Okay, and it can also lose its magnetism. So if you drop it, bash it around, then it can stop being magnetic. And you may remember from experiments at school, sometimes the magnets we use aren't actually doing what they're meant to, and that's because they've lost that magnetism and they need to be reinduced to make them magnetic. Okay, now here is a picture of the Earth, and as I said earlier, and as you may know from geography or from science, year 8, the Earth has got a big iron core going through the middle of it, which is magnetic, and then that causes the Earth to have magnetic field lines, and then that links in with the aurora borealis because that is what effect caused by the magnetic field. So you get this wonderful effect in the sky caused by the magnetic field. Okay, so that's that, and you can see that the lines are going in at the top and they are coming out at the bottom. And if you've remembered back to what I said about the magnet, you'll realize that something's not quite right there, which is why I'm showing you this picture here. So there's our bar magnet, and it always comes out of the north and it goes in at the south. But if you look at our picture of the Earth, it's coming out at the bottom and it's going in at the top. Okay, and I'm just going to show you. So if I put it that way, we've got it the right way round. So magnetic north is actually a south pole because the magnetic field lines come in. And the way I sort of think of it is when we use a compass, we want to find the north. So opposites attract. So north on a compass will point to south because opposites attract. I don't know if Sir's got any other bits that he wants to add in on this bit, or...
No, although if you're looking for an extinction activity, you might go and have a look at the evidence that the magnetic poles of the Earth have flipped in the past. Interesting topic.
I might go and look up that after we're done, so. Okay, so that's that, just to let you know. And also the magnetic pole can shift slightly. Again, that might be something you want to look into, but that's just extra information. Okay, I'm going to bounce us on. So that was magnets done very, very quickly, but hopefully it's recapped you from stuff you've already done before. And you got the key take-home messages about drawing the field lines with going into south, out of north, and making sure you've got those arrows on and that you can draw these loops. Okay, I'm now going to move us on to electromagnets, and you will need to be able to describe the key features of an electromagnet. You'll need to be able to draw magnetic field lines and compare patterns from solenoids and straight wires, and I'll explain that, and then look at how you can actually increase magnetism in a solenoid. Okay, so that is what I'm going to move on to now. Okay, and here we've got our electromagnets. Okay, and they differ from normal magnets in a major way. They are made from passing an electric current through a wire that has been wrapped around the iron. So you can see that it has been wrapped here, and this creates a magnetic field that magnetizes the iron core when the current turns off. Okay, hopefully that has helped. Just trying to figure out what I did with the video. I don't know if I've disappeared from your screens, but never mind. Okay, so electromagnets. Okay, there we go. Electromagnets, this is essentially our basic electromagnet, and they're made of the 3 C's. So if you're trying to remember what they're made of, these are the 3 bits. Electromagnets have a core, and it's normally made of a soft iron. And if you remember, iron is a magnetic material. They have a current, which is a flow of electrons, flow of charge, linking back to P1 there. And you can see here I've represented it with a battery. And they have coils. And these coils are usually copper wire covered with an insulating material. And then the coils bit is the solenoid. Okay, so an electromagnet, 3 bits, the current, the core, and the coils. And to explain the solenoid bit a little bit more, I've put this up for you. So electricity is passed through a coil of wire. The coil has a magnetic field around it, and that is the solenoid. So the solenoid bit is the coil of wire, which develops a magnetic field and is a solenoid. And then an electromagnet is when you take that coil and you put it round a iron core. Okay, hopefully that's nice and clear for you, because that's something I used to get muddled on. Okay, why does this all work then? So what is actually going on? Well, we've got electricity moving in one direction in the wire, okay? And when the electricity is on, it causes the material to line up. So you can see here, we've got the same idea of the little mini domains. When you turn the electricity on, they all line up, and it allows the magnetic field lines to appear, and it becomes an electromagnet. This is a really important feature because it means that electromagnets, key point here, can be turned on and off. When they're off, the magnetic fields aren't there. When they're on, the current causes it to come on. Okay, I am going to carry on. Okay, so this is the bit where I would actually like to jump to Mr. Collins, because I reckon he can explain it a lot clearer than me, but it's up to him.
Yep, I'm very happy to do a bit of talking. So hopefully you can still see the slides there, and the first part to look at is in the top left with the picture of someone's hand doing this. Now, it's really important that you use your right hand for this, your right hand. So get your right hand, and what you need to do is put it with your thumb at 90 degrees to the rest of your hand. The idea here is that when you've got a current flowing through a wire, it generates a magnetic field, and you can predict the shape of that magnetic field by using this right hand grip rule. The idea is you put your thumb in the direction of the current, so going from positive to negative, that's the direction the current flows, and you put that, as you can see in the picture, along the wire. Your fingers then curl around, don't make it like that, the direction that when you close your hand, that's the direction of the magnetic field it creates. So you can see in the diagram that blue circle those concentric blue circles, those are the magnetic fields, and you can tell which direction those magnetic field lines will go by using this, and it's in the direction that your fingers curl when you're closing your hand. Okay, so a single wire will generate a concentric magnetic field like that. Now, if you look at the second diagram at the top on the right, when you get a coil, you get something that has a magnetic field shape that looks a lot like a bar magnet. Now, you might just accept that and go, okay, that's fine, I'll get that. But if you move on to the next slide.
Yep.
This diagram explains why. So if we look at the piece of wire just below P, Miss, if you could just move your cursor over that, that's there. Now that piece of wire is coming out of the page at you. So if you get your thumb and put it from your screen going out and curl your fingers round, you'll see that they make that shape you can see in the small concentric circles around that piece of wire. It's creating a magnetic field. The one to the left of it is creating its own little magnetic field. The one to the right of it is also creating its own magnetic field. If you go to one at the bottom, Miss, that one is going into the page. So again, get your thumb, put it in towards the screen you're looking at, and you'll see your fingers curl around in that same direction. That wire and all of those other wires along the bottom are creating their own little magnetic fields along the bottom. Now, what you can see is just outside of those concentric circles, they kind of join up. If magnetic fields are going in the same direction, they sort of add together to make a stronger magnetic field. So all of those small magnetic fields from each individual wire is creating their own magnetic field, but the overall effect is they're adding together to make those big lines you're seeing, which if you go back a slide, Miss.
Yep.
Which you'll see at the top, give you that distinctive shape, which is the same shape field as a bar magnet. Okay.
Right, sir? Okay, so that is the corkscrew rule. And the other little bit that I just want to point out is that we've also got norths and souths on here, and it comes out of the north, same as the before, and in at the south. And then just a little note that I'm reading in the book because I want to make sure. The south pole end is where the current is clockwise, and the north pole, it is anti-clockwise. So I just wanted to give you that key pointer. Okay, so I think we've covered solenoids in wires. Okay, so I'm just going to move us on. Investigating electromagnets. This sometimes comes up with pictures of electromagnets and paper clips, and they will say about how many paper clips are attracted to it. There are several things with these experiments that you need to be aware of. So they will ask you, how can you make an electromagnet stronger? Increase the strength of the electromagnet. One of the ways is to actually increase the number of coils. And if I'm right, sir, that links back to what you were just saying with the little mini electric fields that are generated. So more wires equals more of those little mini fields, and then they can add up to make one big field. So one way to increase the strength of an electromagnet is to add more coils, and the other one is to actually increase the current going through it. But generally speaking, we talk more about the number of coils. The key thing with these, always keep the other bits the same. So if you are changing the number of coils, you would want to keep the current the same, keep the core the same. And we don't normally talk about changing the core in electromagnets. Oops, excuse me. Okay, so we talk about the current. Now I've got a little poll just to check you were listening to that bit of how can we increase the strength of an electromagnet, and hopefully you're all going to be all right on that one. Okay, and hopefully I wasn't sharing that the whole time. Right, there we go. Go launch. So how can you increase the strength of an electromagnet? Hopefully that has launched. Could you use a different core, increase current, increase the number of coils, or use a non-insulated wire? And I threw that one in there because hopefully you think. Again, if you've got any questions, what you've seen, Mr. Collins is there. He is happy to answer them. Don't know if you have.
Yeah, the only question we've had so far was, are electromagnets an induced magnet? and we classify them differently. We say there are 3 different types of magnet. You have permanent magnets, induced magnets, and electromagnets. But clearly you can see that electromagnets use an induced magnet. That core in the middle becomes an induced magnet as part of the electromagnet. So sort of, they're kind of induced, but we classify them separately.
Thanks, sir. Okay, and I'm going to end that poll, and I can tell you've all been listening, because increase the number of coils, and then we've got a few on increase the current. So well done, lovelies. Okay, next bit I'm just putting in because it can come up, and it's useful because you need to know how to sort of apply an electromagnet to it. So one of the biggest uses of an electromagnet is in a scrapyard to pick up scrap metal, or in a car junkyard to pick up cars and move them around. Okay, large electromagnets can be used, and they will attract any of those 4 materials at the beginning. So steel, which is often found in cars, iron, cobalt, nickel. The advantages it has as an electromagnet, you should hopefully be able to work out, it can be turned on and off. Okay, so it's not always going to pick up everything. You can turn it on, pick it up, move it, turn it off, and drop what you want to get dropped down. Okay, so that's why I've included that one, just in case you get any questions on uses. I am thinking that actually I have covered everything on this. I'm going to get Sir to jump back in off his mute now, just to check we've covered everything.
Yeah, I think it's probably worth saying, if you feel like this wasn't very hard, this bit isn't hard. Everything we've done so far today has been in the foundation, and so this has to be accessible for foundation students. There is a significant portion of stuff coming up for higher and triple students, which is significantly harder, but that's really, we're going to dive into that next week.
Yeah, so this was just making sure you've got all those basic foundations of solenoids, currents, magnetic field lines, the directions they travel, and all those sort of things before you move on to the trickier bit. Okay. If you have any questions, I can see there might be one in the box, sir.
Yep, I've just had one. Can permanent magnets lose their magnetism over time? They're called, very long periods of time, yes, they can. And induced magnets can lose their magnetism very quickly. That's kind of the difference between them. So yes, over significant, like hundreds, thousands of years, they can. But if you're just talking about like a few days, then no.
Oh, any more questions, or is that it one? If you've got any more questions, do feel free to ask them. I'm just checking the time. It's 11:23, so we're very early on in this one. So we have got time for questions. If you've got any questions about any of the previous stuff, waves. I don't know if Simon's answering questions.
No, absolutely. Anything you got across anything you fancy.
So if you've got any questions on the electromagnets,
okay, do electromagnets have to use an induced magnet or a permanent magnet? The key thing with electromagnets is you want to be able to turn them on and off again. So if you use a permanent magnet, you're not going to be able to turn it off and stop it being magnetic. So you'd always use a soft iron core in the center of your electromagnet, so that when you turn it off, then the domains scramble again and they go back to not being a magnet, so it can drop whatever it was attracting previously. So yeah, in terms of, like I said, this is largely foundation stuff. Some of the higher stuff will be asking you to apply this, or a lot of stuff around sort of graph work. Graphs showing an experiment they've done with different number of coils and different coils, and there's maybe 2 lines on a graph, and you're being asked to explain, to describe or explain what graphs are showing. So the ideas we're covering here are not complex ideas, but they can be made more difficult in the way that they ask the questions. Right. If you create a magnetic field using electricity, is the reverse possible? Yes, absolutely. That's exactly how we generate electricity. Again, this is in the triple content, so those of you who are triple students will actually be studying this in GCSE. But if you need 3 things to generate electricity in this way. You need movement, you need a coil, and you need a magnet. And when the magnet
when the coil experiences a changing magnetic field, and that's going to be a really key phrase for you triple students, it induces a potential difference which drives a current. Now, we are going to go through that. I believe Ms. Bush will be going through that in the triple sessions, because that is a triple only content. But yes, absolutely, that is how generators work. That's how a turbine, a big fan that's spinning, can generate electricity, by getting the coil to experience a changing magnetic field. Where does the electricity for the aurora borealis come from? That's a really good question. If you go back to the slide showing the Earth's magnetic field, short answer is the sun. The sun is constantly kicking out a stream of charged particles. You might have seen solar flares. Sometimes the solar flare will break and go like that. And when it does that, it catapults out a whole load of ionically charged particles into space. When they get to the Earth, those charged particles interact with the magnetic field. You might remember from P1 in radioactivity, if you have alpha particles and beta particles in a magnetic field, they go opposite directions, because one's positively charged and one's negatively charged. Charged particles will interact with the magnetic field, and so they get funneled to the north and the south poles of the Earth from the Earth's magnetic field. Those charged particles then interact with our atmosphere, which excites atoms in the atmosphere. What happens is the electrons in the outer shells jump up to a higher energy state where they're unstable. They de-excite and jump back down, giving back out energy in the form of visible light, which is what the aurora borealis is. So those charged particles from the sun get funneled to the north and south pole. They excite atoms in the atmosphere. When they de-excite, they give out light in the colors that show you the aurora borealis. Yes, and you get them at the south pole as well. Okay, haven't got any more questions. We'll just give it a little bit longer in case there's any more questions coming up.
I'm going to stop the recording because
Great.